Orthoses are devices such as arch supports and braces that address a joint or muscle problem in the back or extremities. An orthosis can provide artificial support, prevent or correct a deformity, or improve how a weak or painful area functions. You can buy an orthosis off the shelf or have one custom made. Producing a custom-made orthosis starts with a thorough examination. A certified professional, called an orthotist, analyzes the problem area. In the case of this patient, the feet. After a few manual manipulations to test the range of motion and pinpoint weakness or pain, the orthotist uses various instruments to measure the angles of the different parts of the feet. Then, it's on to specialized devices that analyze foot position and movement during standing and walking, and how body weight is distributed onto the feet. In this scan, the red areas show that more weight is landing on the left foot than on the right. Next, a 3D impression in foam. It goes to the production department, where technicians fill it with plaster. Once it dries, they extract an exact model of both feet. Now they can construct the orthosis piece by piece. Most of the components are made of different types of polyurethane, a lightweight thermoplastic. Each type is designed to produce a specific effect at a different phase of the patient's footstep. For example, the blue base is made of rigid polyurethane that holds the foot in the correct position. At the front, dense black polyurethane helps propulsion and reduces stress on that side of the foot. They cover the assembled orthosis with a sheet of glue and put it into a vacuum press. The press applies heat to activate the adhesive. It sucks out the air between the components and compresses them tightly together. When the orthosis comes out, they place it on the model of the corresponding foot. Then it goes into a different vacuum press to mold it to the shape. They add made-to-measure corrective parts in latex foam. Then, using hypoallergenic glue, line the orthosis with a soft polyurethane. All that's left to do now is buff the orthosis. This smooths all the surfaces. To ensure the orthosis delivers the goods, the patient redoes the key test while wearing it. Remember that scan showing red areas? They're gone now because the patient's feet now bear her body weight equally. This patient has arrived with a doctor's prescription for a knee brace. The orthotist analyzes his mobility, flexion, and balance, then sends the technical specifications to the production department. There, technicians make a model of the leg. They begin by positioning the leg at a 12-degree angle and wrapping it in plaster bandages. While waiting for the fast-set plaster to harden, the patient chooses a decorative pattern for the outside of the brace. The hardened cast serves as a mold. Technicians pour in plaster, let it harden, then remove the cast. After smoothing the surface, they draw technical markings, then install the lightweight aluminum joints that'll enable the orthosis to bend. Now they run a sheet of plastic through an oven. This is high-memory plastic, meaning that when you form it, it remembers the shape and maintains it. The design the patient chose comes printed on transfer paper. They use a laser thermometer to ensure the plastic is at the perfect temperature for the pigments to penetrate properly. They carefully position the hot decorative plastic on the model. Using a vacuum bag, they remove the air and press the plastic on tightly. The plastic sets in about 2 minutes, maintaining the form. They cut the required shape, line the inside, and sand the edges smooth. Finally, they attach straps to fasten the orthosis to the leg. The orthotist checks the fit on the patient, then runs various tests to make sure the orthosis is doing exactly what it's designed to do.
The ancient Romans and Egyptians fashioned artificial eyes out of painted clay. By the 1500s, Europeans started making them out of enameled gold, and soon out of glass, which remained the norm for hundreds of years. Today, most artificial eyes are made of acrylic. If you've lost an eye in an accident or to a disease, a specialist known as an ocularist can fit you with an artificial eye. You can get a ready-made model or a custom-made prosthesis like the one for which this patient's being fitted. No two people's eye sockets are the same, so the first step is to take an impression. After inserting the impression tray, they inject a material called alginate, filling the entire socket cavity. After 90 seconds, the alginate sets, and they can remove the hardened impression. They place the impression in a mold and pour in a type of plaster. When the plaster has hardened, they remove the impression tray and then the impression itself. What's left in the mold is a plaster replica of the socket. Now they put a wad of acrylic plastic dough into the mold, lock the mold into a press, and submerge it in a high-pressure curing unit for 25 minutes. Then they cool the mold in cold water. Here's the original impression compared to the acrylic model they've just cast. This model is called the fitting shape because they use it to fit and mark the positioning of the fake iris. They accentuate the markings, then attach a peg with a drop of wax. The peg indicates the natural angle of the iris when the patient is looking forward. Next, they add wax around the perimeter to enlarge the fitting shape. This excess will give the ocularist some play afterwards for the final sizing. Now they take this marked and enlarged fitting shape and make a plaster mold. They'll later use that mold to cast the actual artificial eye. But first, they have to make the iris. They take a curved black acrylic disc and paint it as realistically as possible with high-quality artist's oils. The patient has to be present so they can match the real eye. Next, they glue an acrylic cornea with an appropriate size pupil onto the painted iris. At this point, the artificial iris is 13 millimeters in diameter. If the patient's real iris is smaller, they trim down the replica to match. The iris then goes into the plaster mold, covered with white acrylic dough. After the same high-pressure curing process as before, out comes the artificial eye, covered with excess white acrylic. They trim off that excess and the peg, using a grinding tool and a cutter. This refines the shape and exposes the iris buried underneath. They smooth the surface against a grinding stone and verify the measurements. Then, using hard coloring pencils, they add finishing touches to the iris and draw blood vessels. They label the eye with the patient's initials, then apply an acrylic coating to seal the pencil marks. To create veins with some dimension, they use the same acrylic coating to stick on some delicate silk threads. Once they're satisfied the artificial eye is a perfect match, they seal the artwork with another acrylic coating. Once that cures, they polish the eye to a shine with a cotton wheel. The shapes and colors of artificial eyes are endless because patients' eye sockets and irises greatly vary, as do their scleras, the white of the eye. This artificial eye, or ocular prosthesis, is ready. The final step is to ensure that the fit is perfect. The patient's ocular muscles attach to the implant, enabling his artificial eye to move in unison with his real eye.
Making a nylon stocking takes only a few minutes. However, it's a complex operation that involves the knitting of 5 to 8 threads as fine as a hair. The threads, usually nylon and spandex, strong and elastic, are used. Sometimes polyester or cotton are added. The knitting machine goes into action. This one fashions a tube for sheer stockings in 90 seconds. In 3 minutes, it makes a tube for tights. Its speed is adjusted according to the product being made, varying between 750 and 1200 revolutions per minute. Once the tube is knitted, it is sucked up and lands in a bag where it will be inspected. More than 500 machines share the work, each making a model that is specific for it. The two ends must now be joined. This automated machine assembles the two tubes together to form the pantihose. Then a scissors cut the pantihose, a necessary step in production of a pair. This opening is enlarged to allow for sewing, which will join the two tubes at the point of the panty. The label with the size or brand name is already sewn in place in just 10 seconds by this robotic machine. At this pace, it sews on 4,800 labels in 8 hours. Installing a gusset requires some preparation. A scissors makes a hole at the joining point. Then the stocking is turned inside out by suction so that certain stitching can be done on the inside. Thus, these stitches will be less visible. Now the foot must be sewn. This robotic machine places the foot in position. Then a sewing machine makes stitches at the same time that it cuts away excess material. This step requires only 10 seconds. Then the pantyhose is turned right side out, again using suction. Everything is ready for installation of the gusset. The pantyhose is placed in a tub and taken to this department. The stocking is again suctioned and placed on a gusset machine by the operator. This method assures that the gusset will be installed well-centered without a pleat. Putting in the gusset is the final operation in the process. A pre-cut piece of cotton is slid into the space reserved for the gusset and automatically sewn in. Only aesthetic touches remain, such as adding a little color to the pantyhose. They're placed in this machine, which has a large drum with 4 compartments and a 45-kilo capacity. The pantyhose are washed in soapy water, then immersed in dye. Temperature climbs gradually to 93 degrees centigrade. After a 5-minute rinsing cycle, a softener is added. This all takes 2.5 hours. Once dried, they proceed to inspection. The pantyhose is placed onto a form which stretches it to allow inspecting for any imperfection. If all is well, the pantyhose is transferred onto another metal form where it will be pressed. The pantyhose is positioned, guided by a magic eye. The pantyhose is then carried toward a steam room, remaining there for 2.5 seconds before being dried in 7.5 seconds at 140 degrees. They fold and pack 420 pantyhose per hour and make 180,000 pairs per day.
You could say that interlocking concrete pavers came out of the rubble of World War II. In post-war Holland, there weren't enough clay pavers to rebuild city streets, so the Dutch began making concrete pavers. The Germans refined the technology and exported it to North America, where they found a quick road to success. Call it a concrete solution for paving. These pavers are solid, and the interlocking design disperses weight, easing the load on the road. To make these pavers, a conveyor belt delivers concrete sand to a weigh belt that weighs the coarse sand as it falls onto it. The weigh belt carries the sand forward, while another conveyor belt unloads stone chips to be weighed. These chips are no larger than 1/3 of a centimeter. The ratio of sand to stone chips varies, depending on the type of paver being made. The weigh belt transports the stone chips forward, along with the coarse sand. Both are en route to the skip hoist. They spill off the conveyor into the skip hoist, which is essentially a bucket on rails. Cables pull the loaded bucket upwards. It stops about 9 meters up, just above a big concrete mixer. A trapdoor opens and dumps the sand and stone chips into the mixer. 6 giant steel paddles mix and then rotate and mix again, while cement is added automatically through several nozzles on the side of this enormous mixing bowl. Making pavers is a bit like baking cookies. Too much or too little liquid in the batter and it won't bake properly. Water is added until the consistency is just right. Nozzles also shoot a pigment into the mix to tint it. The mixture looks dry and crumbly, but the recipe gives it just enough moisture to form the concrete. Now a filling wagon spreads the mix over a steel mold containing up to 50 paver-shaped cavities. The mold press head applies 10 tons of vibrating pressure. This pulsating force compacts the mixture into the paver mold and removes any air pockets, which could weaken the pavers. Hydraulic cylinders lift the mold, leaving the pavers on the press board. The press board slides out and the mold once again gets filled in and makes another 50 paver stones. It only takes about 10 seconds to mold, compact, and release a batch of pavers. The press boards filled with pavers slide into a rack. A hydraulic chain hoist lifts each board into a large holding rack. There, a special moving wagon called a finger wagon picks up all the boards from the rack in just one move. The electrical wagon moves along a rail to a curing kiln, where it's almost 38 degrees Celsius. The pavers actually generate the heat due to a chemical reaction from the combination of cement and water. About 12 hours later, the finger wagon carts the pavers out of the kiln. They're now 70% cured as a result of the chemical process that binds the cement, sand, and gravel, causing the pavers to harden. The rest of the curing will happen over the next 28 days. The pavers are now sturdy enough to handle, so 4 steel arms with rubber pads move in and straighten the stones on the board. These alignment arms are hydraulically driven. They arrange the concrete pavers so they interlock snugly. Now, hydraulic clamp arms lift the pavers off the board and begin to pile them up. They're making a cube of stone. This stacking machine is called a cuber. It packs 9 or 10 layers of pavers on top of one another to make this cube. The cube is actually called a bundle. It will be strapped and shipped out to the job site. These concrete pavers will be on the road soon, in more ways than one.